Alright folks, hello and welcome to this video lesson on section 2.5 direct variation. In this video lesson we'll go over some definitions, some examples, and see how to apply it in the context of a word problem regarding the language of direct variation. So let's get started. A direct variation is a function that can be represented by an equation of the form y equals kx for some constant k. Now they chose k, but it didn't have to be k. K is called the constant of variation, as is written here. But if you'll notice, this equation looks eerily similar to the slope-intercept form equation y equals mx plus b. However, there is no b written. Or in other words, b will have a value of 0 in the direct variation equation. Or in other words, if we were looking at it on a graph, the y-intercept will always be 0. And if that's the case, then we know our graph is going through the origin. So in any direct variation, we can conclude, and I would jot this graph down, that the direct variation will always form a line, since it's y equals mx, okay, which is the equation of a line, and that line will always travel through the origin. Now, it could have a positive slope, it could have a negative slope, it could technically even be flat along the x-axis. Those could all count as direct variations, but you're going to have to look at the problem on a case-by-case basis. To take a look at an example that would not be a direct variation, well, first of all, any type of curve, such as a parabola or a cubic function, are clearly not direct variations because they don't form a line. And secondly, even if you did have a line but it didn't pass through the origin, something like this would not be considered a direct variation either, because it would have a y-intercept that's not 0, and therefore it could not be written in the form y equals mx or y equals kx. Now, look at some more examples of how to tell from an equation whether something's a direct variation. Let's copy these into your notebook. Looking at number 1, we have y equals negative 8x. That is a prime candidate for a direct variation because it's already written in this form for some k, and in this case the k equals negative 8. So we can indicate that this is a direct variation. Okay, next up we have this equation, y minus 4 equals 3x. And at first glance it does not look like a direct variation because it's not written in this form, y equals kx, but be careful, because sometimes it may not start out looking in that form, but it can be manipulated to look like that form. So let's try to isolate our y and see what happens. If we add 4 to both sides, we get y equals 3x plus 4. We did our best, and we did not get a direct variation because quite clearly here the y-intercept is 4. So this is not a direct variation. Next up, we have 6y equals x, and isolating y like we did in the last equation, we will arrive at y equals x over 6. So this does appear that it can be written as a direct variation. We just need to remember that x over 6 can be rewritten as 1/6 times x. So this would be the form of the direct variation. The constant of variation would be 1/6, and it does indeed fit the bill of being in the form y equals kx. So we can say, yes, this is a direct variation. Last but not least, let's continue with that technique of isolating y. So for number 4, we'll add 5x to both sides, and then we'll divide both sides by 2, and we get y equals 5 halves x. This does fit the format of direct variation, where the constant of variation is 5 over 2. So this is indeed a direct variation. So I should be able to give you an equation with y and x, and you should be able to determine if it is indeed a direct variation or not. Next up are some word problems, the language for word problems. You'll be doing some problems on the recommended practice, but for now I just want you to get used to seeing the language. So when they say that y varies directly as x, if they say that in a problem, they're saying that y will equal kx for some x. So x would be considered the independent variable, and y would be considered the dependent variable. You don't need to get too hung up on those terms now, but you should know them, and you're going to be able to determine which variable is which depending on how they word things. So that one's easy. Y varies directly as X. Or they might say something like this. C varies directly with H. In that case, H, if C varies directly with H, well, it's kind of like Y varies directly as X. C is varying directly with H, meaning that H will be the independent variable, and C will be the dependent variable. But honestly, if you're not sure, you can still end up writing a direct variation equation. Let me show you what I mean. Say you set it up correctly, C equals K times H for some K next to H, and then you go to solve the equation like that. Well, that's all great and fine, and you would get a good answer. But suppose you thought that C was independent and H was dependent, and that was reversed, and you set it up like this. H equals KC. Well, that's still going to be true. All right, that's still going to be true. It's just the value of K is going to be different in each of these. So you could still solve the problem using an equation like this if it's a word problem, and you could find some unknown values, but try to stick with the language and the order that things are written to write it correctly. So if it's written as Y varies directly as X, or C varies directly with H, technically the dependent variable will be listed first, and the independent variable will be listed second. They might follow this convention if they say that S and P show a direct variation, but technically this is ambiguous. You don't know which one is dependent and which one is independent, so you would just pick an equation and solve accordingly and get a K according to that. But there's no right or wrong answer like there was over here when it was worded a certain way. So just keep that in mind when you're looking at word problems later. You're going to see different variables and things varying, and you want to get it right for writing that formula. Alright, so let's recap what we saw in this video lesson. First, we defined direct variation as an equation in the form y equals kx, and remember we said that it must pass through the origin and look like a line. Sorry, I missed the origin there, but you get the idea. Second, we said we decided how to tell if something's a direct variation. By isolating y, we can see if it fits the form of y equals kx, and if it does, then it's a direct variation. If it can't be written in that form, it is not a direct variation. And last but not least, we looked at some word problem language and how to determine if something's dependent or independent and set up your formula accordingly. With these three concepts, I will recommend the following practice on page 109 to 111, 11 to 41 odd or odds, and I want you to omit numbers 17 and 37. And that's because all the answers can be found in the back of the book except for those two. So I'd recommend that you try these and check the answers on your own. I'm not going to do a formal homework check in class, but I will take any questions on this assignment, and we'll be doing some more problems with direct variation on Monday. Thanks for watching this video lesson.